All right, this video is going to be all about the force of kinetic friction. So let's jump right into it. So the symbol that we're going to use, which we've introduced already, is a big F for force, little f for friction, and then little k for kinetic. Right? So the force of kinetic friction is force kinetic friction. This is the force that opposes sliding. And I'm using that word sliding very carefully. I'm purposefully not using the word moving because we're actually going to see some situations where the force of static friction causes something to move. So really, when we're talking about the two forces of friction, we're talking about either preventing sliding relative to the surface you are on or opposing sliding relative to the surface you are on. So that surface could be the ground, that surface could be a wall, it could be a ramp, or it could be another object. Like if we have two objects stacked on top of each other, we could oppose or prevent sliding between these two blocks. Okay? But the force of kinetic friction is the force that opposes sliding relative to the surface. Unlike the force of static friction, the force of kinetic friction is a constant value. So we don't have to worry about any inequality symbols or anything like that. There's just going to be an equal sign. So it's a constant value no matter that opposing force or speed. Okay? So it doesn't matter how fast or slow we're going, the value we calculate for the force of kinetic friction will be the same as long as we keep the other variables that friction depends on the same. So much like static friction, we're going to have a coefficient of kinetic friction. Again, this is the Greek letter mu. I think of it as like an M and a U combined. Sometimes it looks like a really fancy U like that. But this is the coefficient of static, or no, wow, oops. It's coefficient of kinetic friction. Okay. And this again is a measure of how rough the surfaces are when sliding against each other. Now, no matter the surface, this coefficient of kinetic friction, mu k, as you'll sometimes hear me refer to it, this is always going to be less than the coefficient of static friction. So when we're dealing with static friction, we're kind of thinking about how many peaks and valleys there are, right? And we kind of have to fight and go over each of those peaks and valleys. That's what's happening kind of at a microscopic level. Once the object starts to slide, those peaks and valleys become a little bit more rounded. And because they're a little bit more rounded, it's a little bit easier to pull the object, or the coefficient of friction becomes a little bit less because we've rounded out those peaks and valleys. So this is meant to represent US, this one's meant to represent UK. And so what that means is that we must apply a larger force to get the object to slide than needed to keep it sliding at a constant velocity. Okay. So if you've ever moved heavy furniture, you've experienced this. We know that, like, to start sliding something, we kind of got to give it a little extra oomph before it starts to slide. And then once it's sliding, we actually don't have to keep pushing as hard. So that's because of this fact, the fact that the coefficient of static friction, and therefore that maximum static friction force, is greater than the coefficient of kinetic friction. So it's harder to get something to slide because of friction than it is needed to keep it going at a constant velocity. All right, so our last variable that's going to matter is, again, one that we talked about with static friction, and that is, of course, the normal force. Remember, the definition of the normal force is the force perpendicular to the surface, pushing upward, or pushing, it's not always upward, pushing on the object. Okay. So that normal force is always perpendicular to the surface. It is an interaction between the surface and the object. So there's a normal force on the object, and there's also a normal force on the surface. And if you remember, we kind of said that this helped us measure how pressed together the surfaces are. Or at a microscopic level, how intertwined are those bumps and ridges? Are they barely intertwined, meaning a low normal force, or are they very intertwined, meaning a high normal force? So those are the three variables that we're going to care about with the force of kinetic friction. And like I said, the force of kinetic friction is a constant value, and therefore the equation is an equation, not an inequality. So the equation is going to be the force of kinetic friction is the coefficient of kinetic friction times the normal force. Now make sure that at the end of the notes you add this to your reference table. Right? Not only the equation, but what the units or what the variables mean. You should have normal force there, so you'll just have to add one for FFK and mu K. So again, this equal sign tells us that we are a constant value. So as long as the normal force or the coefficient don't change, the force of kinetic friction is not going to change. Now, one thing to keep in mind is that the normal force may not always depend on the mass, right? Like we've seen with objects pressed against walls, the normal force has nothing to do with the mass of this object and everything to do with the force applied horizontally on the object. So just keep that in mind, that depending upon the situation, changing the mass might have no effect on the force of kinetic friction. So when we talked about static friction, we talked about the graph of the opposing force versus the force of friction. So the opposing force is just whatever force points in the opposite direction of friction. It might be an applied force, it might be a tension force, it might be a force of gravity, like the situation with the wall. So we're just going to call it a generic F opposing. So the first half of this graph we have already talked about, right, where the graph looks something like this. So for this section, this is when our object is at rest. We have not yet overcome the maximum force of static friction, which we can calculate by doing the coefficient of friction times the normal force. So for this section, the force of static friction is less than the maximum force of static friction, so we are not sliding, and therefore the force of static friction is going to equal whatever force or forces are opposited, because we know that the net force has to be 0 in order to keep something at rest. Okay. So this is the part where the force of static friction is variable. Okay. Once we reach that maximum static friction force, the force of friction value drops down because now we're dealing with the force of kinetic friction. And like I said, the force of kinetic friction is going to be less than the maximum force of static friction because the coefficient of kinetic friction is always less. So the force drops down, and no matter the applied force, stays at a nice constant value. Right? So this is now where we have a force of kinetic friction, where we're at a constant value. And at this point, our object would be sliding relative to the surface. Again, I don't want to use the word moving because it's really the sliding that's important. Okay. So if we have an object at rest, we have to apply a force. As we apply a force, the force of static friction increases in response until we reach the maximum static friction force. Then we sort of break free or overcome the maximum force of static friction. And at that point, the force of kinetic friction takes over, and no matter our applied force, the force of kinetic friction is going to be a nice constant value. Okay. And again, this graph shows why it takes more force to get something sliding than it does to keep it going, right? This maximum static friction force is greater than the force of kinetic friction. So you might be trying to figure out, like, which one do I use? Do I use static or do I use kinetic? Do I have to consider both? Right? Well, we're going to know based on the context of the question. So if the question tells us that the block is sliding across a surface or something like that, we know it's going to be the force of kinetic friction. If the block is at rest relative to the surface, the force of static friction is going to be present. Right? Now, we may have a situation where we don't know if the block is sliding or if the block is at rest, or maybe the block is starting at rest and we need to figure out, will it move? Okay, so we can add to that will it move process. So remember, in order to figure out will it move, we have to know the maximum force of static friction, which we calculate by doing the coefficient of friction times the normal force. And we have to figure out how that compares to the opposing force. Okay. So if the opposing force is less than the force or the maximum force of static friction, less than or equal to the maximum force of static friction, the object is not going to move. No. Right? And at that point, because we are at rest, we know the net force has to be 0, so our force of static friction will equal whatever that opposing force or forces is. So that's when we're in kind of this section of the graph. As soon as the opposing force is greater than that maximum static friction force, we now transition to this part of the graph. Right here. And if that's the case, then the force of friction we're dealing with is kinetic friction, and we need to calculate it using the coefficient times the normal force. Now remember, if we are at a constant velocity, then we know the net force is 0. So that would be a situation where the force of kinetic friction is equal to any opposing forces. So we could calculate it that way, but that's only if we're at a constant velocity. Remember that the force of kinetic friction is also the only force that tells us what direction an object is moving based on a free body diagram. Okay. For instance, if I have, let's say we have a situation that looks like this, where F1 and F2 are applied forces, right? And this is on a frictionless surface, so I might write that as mu equals 0. Okay. Based on that free body diagram, I have no idea what direction this object is moving, because free body diagrams cannot show direction of motion. With one exception, we talked about this in class. If the free body diagram has a force of kinetic friction, or even a force of static friction, we can tell the direction of motion, because the force of static friction, or sorry, force of kinetic friction is always opposite the direction of motion. So if my block is sliding to the right, then the force of kinetic friction is left. So that works vice versa. If the force of kinetic friction is left, then the block must be sliding right. Okay? If we're on, say, a ramp, and the block is sliding up the ramp, then that must mean the force of kinetic friction is pointing down the ramp on the free body diagram. Okay. Forces of friction always oppose sliding or prevent sliding. They are always parallel to the surface. So I should never have a force of friction that is off at a weird angle relative to the surface. So think about it this way. The force of friction, whether static or kinetic, is always perpendicular to the normal force. And since the normal force is perpendicular to the surface, force of friction is always parallel to the surface. They must be perpendicular to each other. So that can also help me figure out some stuff. Okay. Now, one thing to also keep in mind is, because no matter what coefficient we're using, that coefficient is usually less than 1. That also means that our forces of friction are usually less than our normal forces. So that is one thing to keep in mind if you are doing a scaled free body diagram. That might be something that is helpful if you want to have the y direction and x directions correspond to each other. It might be helpful to remind yourself that the force of friction is less than the normal force, because that coefficient is less than 1. All right, so I might draw my normal force 3 and my force of friction 2 boxes. And that's about it. I will see you guys next time.